This tutorial is about how to set up problems, form finding problems with constraints on the coordinates of nodes, just the controlled position of these nodes. So we do this along this Schleicher-Bergermann and Partners benchmark with a pedestrian bridge, where we have an arch which is suspending the deck of this bridge. What you see here, that's the final goal, what we like to have. The deck nicely on horizontal here for coordinate z equal to 0. And we would also like to control the apex, the highest point of this arch. Also, we have self-weight applied to the deck of the bridge, and that's what we like to model now. Let's go to the curation sheet, and you see we start with a very much distorted geometry. That's to show you the success of Stiff in the final. But here we would like to set up now this problem. First of all, we have to activate the possibility to give in coordinate constraints. So we go to theory, GUI options theory, and there you see activate coordinate constraints. Otherwise, we will not be successful. Okay. So with that have done, we can now start to give in the goal coordinates. So let's go to the apex, that will be the highest node. Double click to this node to activate its properties, and there you see we have now activated these cells here at the bottom of this menu. So for this node we would like to control the z coordinate, and with respect to the definition of our coordinate system, we would just to have it at z equal to -8, and we give this control, this constraint, the ID 1. Here we can give in some numbers what you like. They must not be in sequel order. They simply are tags, so we can refer to this respective constraint. So we save it, and now observe here my cursor here. And you see here that z equal to -4 and z equal to -8 would be somewhere up there. So that's where we like to lift, let's say, the arch while form finding. We have activated that node, and you see simultaneously all these elements of the arch have been highlighted. Deselected here. So, and selecting it again, you see that all these elements are highlighted. That means all these highlighted elements we would like now to be modified with respect to their force densities while we would like to optimize the problem. Let's check what we have to get in, give in for in elements. So let's start with this element here, bottom left. So double click, we enter this menu for this element, the property menu. Let's go to the loads here of this element here, loads, and there you see we have now this cell here activated, where we can just now refer the modification of the force density of this element with respect to the ID, the constraint ID of our apex node. And you see also it's highlighted, this node, so we can directly see to which node this constraint ID is now referring. It's referring to that. And that's what we're doing for all elements along the arch here. You see now this element has been selected. We check it, yes, okay. It's also related to constraint ID 1, and then we can go across the complete arch to give in this data or check it as null. Yeah, that seems to be okay. Let's now take a look, as an example at least, with respect to the deck here. Let's go to this node and just open the property menu by double click. Again, we go to the Geo tab here and check what's given here as data. You see goal Z is 0, the control number, what you like to achieve at the very end. And you see we have given here the ID number 3. And you see also here already highlighted the respective element where the respective force density has to be modified just to reach the goal that the set coordinate of these nodes should approach to 0. Let's go to another node. For instance, this one here along the deck. Again, the goal value of z is 0 to have this horizontal deck. And you see in this example we have just defined the respective ID to be 8. So when we just go on with all necessary input to control the deck, here for instance this node, again goal z is 0 and the ID is now 12. We have further constraints in this problem with respect to length of elements, and here's in top view the deck, which is supposed to be this S-shaped, and here we would like to control the element length is. Let's look at this element here. You see we have activated the goal length of this element, which is supposed to be 2.5. We can just go to other elements along the deck. This here, there we have the length 2 here. Go further on to this element here, we have now again 2.5 and so on and so forth. That's about how we just curate the input of our problem, and now we are ready to go for form finding. Let's check the options of our technology. We have already given some value for the stabilization factor. I just take it away to show you what happens if we don't take it, and also I switch off the line search and just let's try to optimize form find the problem. And you see it's highly non-convex, and it seems that we have to modify the problem a little bit just to stabilize this. We can start with the stabilization factor. This possible modify now directly optimizing on the augmented Lagrange function. You see we have been stabilizing the problem of just the convergence a little bit, but not successfully, completely successfully. We just add some line search options with another penalty factor. I know it, that is a good value. We can try it with 10 here and see what happens. It converges to the proper solution, what we like to achieve in 12 iterations together with 6 line search. To convince you that it makes sense to check it a little bit, try it around. I try it now with 100, and it seems to converge to another solution which we don't like, because we have this let's say double S bend deck, which is not what you like to have. It's not completely converged already still, but you see by playing around with the stabilization factor and the line search penalty factor, let's try one here, we can just explore the design space. Again, it seems to converge to another solution which we don't like to have. And by that, we can steer a little bit with playing around with these factors, these penalty factors, stabilization factors, that the problem nicely is converging to where we would like to arrive. Last not least, it remains that we check if we are really successful. Remember, the goal was that the apex should be at z equal to 8. Visually it seems to be okay, but let's take a closer look, double click at the node. We see here the original coordinates of this node. We have been starting with -5.81. If you press default, you can see the actual values, which is exactly what we like to achieve, -8 for z. That is okay. Let's also take a look at one of the deck nodes, perhaps this one here. Let's edit it. Again, you see we have been starting with z equal to 1.13. Deformed, yes, we are successful and we have reached the goal. Let's check the length of elements. So this had been, if you remember, the goal length 2.5. For that we have to activate here the display of element forces n here. Let's modify the projection. Let's go into XY. And let's go here for the for the displayed value should be the length. Here we are, and you see, wow, yeah, successful. The length of this element is 2.5. That one as well. This one is 2. Are exactly those values what we have been prescribing. To convince you, let's go into the property sheet of this element. Here you see the goal length we would like to achieve is 2. Wonderful. Okay, thank you so much. See you later.